Okay, what's up, everybody? Welcome back to Proof, Set Theory, and Logic. Another fun day. So, this microphone is really strong today. Let me turn down the gain a little bit. It's a little bit too much. There we go. That's better. Okay, cool. So, let's make sure this marker works. Oh, no one erased this board well. All right, so last time we were talking a little bit about the real numbers, having some fun with it. Today we'll keep it going, talk more about the real numbers. So far we've mostly hit their algebraic properties. That is, the real numbers are a field, and so we're proving a couple things about fields so we can understand a little bit more about how they work. Fields are ubiquitous in mathematics. They are absolutely everywhere. As you've seen in your mathematical career so far, most of your study of mathematics has been devoted to fields. In fact, very little of your study has been devoted to much of anything else. Perhaps the only large diversion from fields you've seen is when you studied polynomials, which are not quite nice enough in general, most of the time, most sets of polynomials, to be a field. So let's get back into it and see a little bit more about what's going on with the reals. What we'll end up kind of building to is that the real numbers have all these cool algebraic properties which hook up really nicely with their, you can think of it as, we'll call it order theoretic properties. That is, like the reals come equipped with a very nice ordering, the standard one that you're used to, like which numbers are bigger than other ones. But this ordering is effectively induced by its algebraic structure. That is, like the ways you can put together real numbers with like addition or multiplication and stuff, induces like an ordering on them. And you can kind of obviously see that. Like, when is one number bigger than another? Like, when is, you said A is bigger than B, wouldn't that mean something like A minus B is greater than 0? Yeah? See kind of how you can convert an ordering statement into an algebraic statement? Okay, so there's a nice interplay between the order structure and the algebraic structure of the reals. And this will all tie into something that we won't as explicitly introduce, but that will come up. That is, it's a topological structure. So you've probably, I'm guessing, not, people haven't talked to you about topology yet. Yeah? You haven't had the topology talk. It's hiding in the background of most of what you've done so far at various stages. It's all over the place. We'll get to a little bit more of it later. But basically, there are these, in many ways, I'd say these three discrete chunks that drive most of what's really nice about the real numbers. So let's get back into the theorem we were proving last time. We were doing theorem 6.2 in your notes. So for any real numbers, A, B, and C, we had a bunch of different items. We proved 1 through 4. So I will only write down the remaining ones. 5 said A times 0 is 0. 6, which said that the additive inverse of a real number is equal to the additive inverse of the multiplicative identity times A. And 7, which told us that, 5, 6, and 7, okay, good. That if AB is equal to 0, then A equals 0, or B equals 0, or both. It's not an exclusive or by any means. Okay, so we proved the first 4 of them. Pretty straightforward. And an important fact that I tried to highlight last time, or at least sort of stress, was that none of our proofs really actually relied on the fact that we were talking about the real numbers. These are actually just generic facts about fields. So true for any old field, whether they're like the clock numbers we were talking about last time, or the reals, or the complex numbers, or the rational numbers. There's a lot of different ones. But OK, cool. So let's keep going. So for 5, what would you do? How would you start? I'm actually not sure if I even proved this one in the notes. Oh, did I? Or in the typed up notes, at least. 2, 3, 4. I think I left these last few of them for you. We might as well prove them anyway. Let's have fun. Let's just do it, right? OK, so how would you show that a times 0 is equal to 0? Divisibility rules. Explain what you're thinking. So we'll kind of sketch over here. What are you thinking?
Well, it's for divisibility, you could use this as an example, right? But we're trying to prove that a times 0 is equal to 0, so we can do the inverse of that word.
OK, I think I see what you're saying. So the kind of approach you're talking about is you're basically trying to use some property of 0, right? Along with, say, like a distribution or something like that, yeah? To get this result, yeah? OK, that's pretty reasonable. That's pretty reasonable. So you're maybe trying to do something like, well, here, perhaps we could do something like this. So we know that if a plus b equals a plus c, then b equals c. That was the first item we proved, right? So maybe we could use this, perhaps. Would you perhaps want to do something like that? We could try to somehow construct 0 on one side and a times 0 on the other side. Perhaps we could also do another sort of, yes?
I have an idea. If we substitute the 0 for the additive inverse, so a plus minus a.
This is a great idea. OK, I see your idea here, and I like it. So let's think about what you're saying. You're saying a times 0 is the same as a times a plus minus a, something like this. OK, and what would you do then? Use like distributivity or something? OK, and so you get a times a plus minus a times a. OK. Now, if we had proved item 4 first, if you want to go ahead and prove item 4, we can use this trick. This is a perfectly reasonable way to get there, because then what you'd want to say is something like a times a minus, or I'll say plus minus 1, and then a times a. And if I do a little bouquet of parentheses right there, you can see exactly how I can distribute this. I can just take advantage of the fact that this is, I've got an implicit 1 right there. And I can rewrite this as a times a, and then 1 plus minus 1. And then that just becomes a times 0. What?
Start with 0.
You want to start with 0. I like this idea.
As like minus a times a plus a times a.
OK, so 0 is minus a plus
a times a.
OK, I see where you're trying to go. So what you're trying to do right here is effectively do this trick, where you're saying 0 is equal to 1 plus minus 1 times, say, like a times a. Yeah, and then you're going like, OK, so this is, well, can you do this? Is this a reasonable trick? What I think you want to do is you want to write 0 as perhaps something like, like, are you saying like a plus minus a? Or, OK, you want to do something like this. Use the definition of the additive identity, or of additive inverses, yeah? And then from that, get to, OK, from here, what can we do? well, we could maybe, if we had item 4, we could pull a -1 out. Yeah. And then we could use the definition of the additive identity. I'll even do this to do that trick. And then we could use the distributivity of multiplication to turn this into 1 plus -1 times A. Yeah? Okay. So this is definition of an additive inverse. This is item, what, 6? Okay, this here is the definition of additive, or of multiplicative identity. And then here, this is distributivity. Okay, and then from that, we just get 0 times A via the definition of the additive inverse, since a thing plus its additive inverse is always 0. That's a very reasonable proof. How about we keep that as our proof for item 5 and instead start by proving item 6. I like the way you guys came up with that. That is very clever. Okay, so let's prove item 6 first. Since after all, if we're going to prove item 5 using item 6, we should probably get item 6, yeah? Okay. What can we do? Well, we want to show that these two things are equal. Perhaps we use item 1, which says that if A plus B equals A plus C, then B equals C. That would perhaps be a good way to do it. Let's show that if we add either one of these things to A, we get the same thing. That might work. What do you think? Yeah? Let's do it. A plus minus A is 0, and A plus -1 times A, well, this is just equal to 1 times A plus -1 times A via the definition of the additive, or of the multiplicative identity. It's the thing you can multiply anything by and not do anything with. And then via distributivity, 1 plus -1 here now is being multiplied by A, and this is 0A. And ooh, now it seems like we need to say that that is 0. Uh-oh. So we could use item 5 to prove item 6, but it looks like we've used item 6 to prove item 5. Uh-oh. Does anyone see any other way to get there? So maybe I'm making this into too much of a puzzle instead of just giving you clean, nice proofs and showing you the tricks. But these are actually, I think, the fun parts of trying to get used to writing proofs like this. These things are properties that you take for granted, right? But they're actually not that straightforward to show if you just naively go for it, right? You need to actually come up with a way to get there. So here, we've gotten to some way to say, oh, okay, well, if these two are equal, then that thing is equal to that thing, right? You would perhaps agree with that, yeah? Okay, so we have a proof now for 6, assuming we have a proof for 5, but our proof for 5 uses 6, so maybe we need to do something else. Any of the previous items seem reasonable? Would you agree that minus A is equal to A? We proved that in item 2. So perhaps we could use a different one. That is, maybe if we use item 2, this is a good kind of thing to do, is if you're trying to construct a proof, and I'm trying to kind of just actually go through like the leading you through process here, right? Okay, so item 2, like a good thing to do is to go through and say, okay, I tried something. Here's where it got me. Does it work? If it doesn't, let's try a different thing. You don't actually have that many things available to you to use at this point. It's not terrible to just kind of chug through the few you have. So if we use item 2, which says that minus a is equal to a, okay, now if we use something like this, could we somehow get what we want? That is, could we show that minus a is equal to minus 1 times a? Let's see if we can. Some people are saying no. What if we add minus a to both sides? Right this way. Minus a, this is the thing that you add to minus a to get 0, right? Okay, so I've added the thing you add to minus a to get 0 to minus a. So, here, I'll even do this just to make it more compact. That's 0, right? From the definition of an additive inverse. And on the other side, I had, I added minus a to both sides, so I have minus a plus a. That is also 0, yeah? Okay. Does this do anything for me? Is there any sort of a trick here going on that I could pull back to get a minus 1 somewhere in here? What is anyone thinking?
On the right side, can you pull out a negative 1?
From here?
Yeah.
It's a reasonable idea. If you can use this fact, then indeed we would get what we want. But it doesn't quite seem like we can. Maybe we need to do something else. So, what would you try next? Seriously, just look back in your notes. Look at the different laws and identities you have. What can you do? Yes?
What you just had, couldn't you have taken the negative a plus negative a equals 0, right?
Yeah?
Could you, like, put one on the other side that is
Okay, add a to both sides. You could do something like that. This is true. And in fact, this is item 2. Says that negative a is a. Totally reasonable.
and then like
I see something that you're doing. Okay. So what we focused on so far seems to be trying to add additional terms or something. What if we just focus on this piece right here, this minus 1? What could we do there? Okay. So maybe we could do something like, well, we don't yet know that minus 1, that the additive inverse of the multiplicative identity times an element is the additive inverse of that element. We don't know that yet, right? You can't just move the minus symbol, right? It's not, don't think of it just like the minus symbol. It is ultimately for the reals. But so far, think of minus a thing as being just like a formal symbol, like a different letter almost, right? Like it's like a whole unit. It means this is the thing you add to 1 to get 0. It does not mean like subtract 1, right? Like we don't have a subtraction operation yet. Okay, so maybe we could write some kind of stuff. Like, would you agree that like -1 is, say, something like -1 plus 0, maybe? You'd agree to that, right? And so maybe you could say something along the lines of like -1a is -1 times, or plus 0 times a. And then you could go like, okay, this is like -1a plus 0a. And then could you do something from there, perhaps? Or is anyone seeing any good tricks? I'm just trying to point out that we have only a limited number of possibilities. We've got a lot of heads in this room. We can figure it out, right? Oh, a 0, right? Rewrite 0 as the additive inverse. Okay, so for 5 or for 6? Remember, we have proofs of either one as long as we have one of them. So if someone sees a proof for 5 instead, go for it. That's perfectly good. We could do that. Okay. So are you thinking perhaps something along the lines of taking this and turning it into something else, or? What if we focus back on 5 instead? I don't think we're making progress on 6. Okay, if we go back to 6 and we have 5, we can do it. Remember, we had the trick for it, yeah? So if we have 5, we can do 6. The way to do 6 with 5 is straightforward. We just say, okay, minus a plus a equals 0, and a plus -1 times a is equal to 1 times a plus -1 times a, which is equal to 1 plus -1 times a, which is equal to 0a, which is equal to 0 via item 5. So via item 1? 1? Yes.
That's 5.
Yeah, this is item 5 right here. This is just the definition of the multiplicative identity, distributivity, definition of additive inverse, and then item 5 gives you this. Yeah? Okay, so let's see if we can do item 5 without using item 6. We got 5? Show me. What do we got?
We start with a times 0.
Okay, okay.
We rewrite 0 as the additive inverse.
So you rewrite a as what?
0 as the additive inverse.
Oh, okay, so you have a, and then a, or what? Additive inverse of what?
Plus, a plus minus a, right?
A, okay, okay. Okay.
Then you multiply by the multiplicative inverse of both sides.
Ah, okay, multiplicative inverse of what?
A is -1.
Okay, okay, so you're going to go, okay. So this will require that a is not equal to 0. That's fine, okay. And so then you're going to get 1 times 0 equals 1 times a plus minus a. I like this, okay.
By item 1.
So this is just 0 by the definition of the multiplicative identity. By the definition of multiplicative identity, this is a plus minus a. Okay. That is very nice. I think I see it. Okay, so to put it very slightly more cleanly, Okay, I think I see. Yep. So does everyone see the manipulations that just went on? It does require that a is non-zero. I like the approach you just did here. This is very smooth. Okay, so you went a times 0 is a times a plus minus a. Great. Now we said, hey, check it out. You could write this as a inverse times a times 0. Yeah? And get 1 times 0, which is 0 just because 1 is the multiplicative identity. Yeah? Okay, cool. Now over here, doing the exact same business, we end up with a plus minus a is 0, which is good. So we could almost like reverse engineer this in some ways. That is, we want to do is show that this thing is equal to 0. Yeah? Okay, so we've done a big long string of manipulations now. And we've gotten, well, we should be a little careful, because at one point we multiplied by an a inverse, right? So this thing is not, in fact, equal to the next line, right? What we've really shown in one way is that a times 0 is indeed equal to a inverse times 0. Yeah? I like this approach. This is smart. I like the way you're like splitting this up like this. Okay. We're on, I think, the right track. What other kind of ideas? Maybe we could go even with some silly ideas. Like this is a smart one. This is close, but we should be careful because between this first equality and the next one, we have done something else. Yeah? We've shown that a inverse times a times 0 is equal to 0. That's true. But have we yet got that a times 0 is, through some string of manipulations, equal to 0? Perhaps not directly. Would you agree? I'm kind of spending a lot of time on this, but this is a fun exercise. Would you agree that 0 is equal to, say, like a 0 plus 0? I would agree to that, right? Okay, so would you agree that a times 0 is equal to a times 0 plus 0? Okay, and would you agree from this right here, I'll even write it like this so it doesn't get confused. This thing implies this statement. Now I'm going to do some more equalities right here. That via distributivity, this is a times 0 plus a times 0. Okay, so a times 0 equals a times 0 plus a times 0. Now, 0 is the additive identity, right? So would you agree that a times 0 plus 0 is equal to, well, a times 0? Yeah? Okay, so this is this, a thing plus something is equal to a thing plus something else. Those are equal, right? Okay. We were really close. See how you split it up? Like you split up the part of it, but we were splitting up a's, right? We weren't using the fact that 0 is the additive identity. That's the big important piece of it, is 0 is something you can add to anything without messing anything up. Okay, so 5, we use item 1, which says that a plus b equals a plus c implies that b equals c. Since 0 equals 0 plus 0, a times 0 equals a times 0 plus 0. And since 0 is the additive identity. And multiplication distributes over addition. A times 0 plus 0 equals A times 0 plus A times 0. Hence, A times 0 equals 0. A plus B equals A plus C, hence B equals C. Low on the board, sorry. It's the same computation. Cool? So now that we've got that, this equality right here, which is the item 5, is well justified, and we have item 6 as well. Good. Okay. Yes?
So then, is there a proof for 6 that doesn't require 5?
Okay, a proof for 6 that doesn't require 5. Minus A equals minus 1 times A. Is there one that doesn't require 5? I mean, certainly the easiest one uses 5. Can we think of one that doesn't require 5? I bet we can figure one out quick. I don't want to just turn this whole day into proving this one theorem. However, let's give it one attempt, since that is a great and interesting question. But off the top of my head, I feel like the answer is yes, but I don't remember it. So let's see. Okay, so let's see if we can do 6 without using 5. So we want to show that minus A equals minus 1 times A, and we don't want to use the fact that 0 times A is equal to 0. Could we try using the multiplicative inverse of minus 1, perhaps? Maybe we could do something like this. Let's see if this works. Yeah? Okay. Yeah, okay, here's what we'll do. Yeah, I think this might get us there. Okay, so the idea will be that we'll start with minus 1 times A, and then we'll say, okay, A is equal to minus 1's multiplicative inverse times minus 1 A, right? It's certainly equal to 1 times A, yeah? And you can write 1 as multiplicative inverse times the element, yeah? Okay, cool. So if you buy this step right here, by the definition of multiplicative inverses, this is 1. I mean, maybe there's even like a hidden step right here where I write it like this, and then I go like that. Okay. Now I could potentially try adding minus A to both sides. This work. Okay, yes, okay, here's what we need to use. For this one, we would use item 3. Item 3 from before tells us that if A is non-zero and AB equals AC, then B equals C. Okay, so very close. Man, we are dang close. Okay, let's see. Can we do... There is a proof of this that doesn't use item 5. I am now sure of it. Oh, what is the clever idea? Is it that you write -1 as -1 plus... We don't want to write it as -1 plus 0. That'll throw us some problems. Maybe I should have done this with a minus a. Yeah. Okay, now if we added minus a to both sides, I would get a plus minus a. That's 0, right? And on the other side, I would get -1 inverse -1a, which I'm just going to treat like its own little thing right there. Plus minus a. Okay, so... Oh, man, okay, No, it doesn't quite give us what we want. Okay, I can't think of, I don't want to waste everyone's time while I just stare at the board, but there is a proof of it that doesn't use item 5. I will figure it out for next time because, God, that's a good problem. That is a wonderful little problem. I like that a lot. If anyone else figures it out, I will give you lots of pats on the back for that. That'd be great. So 7, let's do 7 just to finish everything up, which says that if AB is equal to 0, then A equals 0 or B equals 0. What should we do there? Okay, so you're going to say suppose AB equals 0. If A is equal to 0, then either A is equal to 0 or B is equal to 0 is true, right? That is a true statement, right? If A is equal to 0, then A is equal to 0 or B is equal to 0. One of those things is true, right? Okay. If A is not equal to 0, then it has a multiplicative inverse and a to the minus 1, a, b, equals a to the minus 1 times 0. But this just says b is equal to 0. So the result is true even when a is not 0. That is, we've broken it into two cases. Either a is 0 or a is not 0, right? If a is 0, then certainly either a equals 0 or b equals 0. If a is not equal to 0, multiply both sides by the multiplicative inverse of a, and then using item 5, we get that, oh, sorry, this should be b, not a inverse, oops. B times 0 is indeed 0 right there. But a inverse b, this is just 1 times b, that's b. Yeah? Do you agree with this? Maybe? Or is it too compact right there? We can write it out in long form if you prefer. I'm seeing some looks that say, I would like it a little bit more right there. So it has a multiplicative inverse, and we have that, well, b, would you agree, is certainly equal to 1 times b? Okay. And would you agree that 1 times b is equal to a's multiplicative inverse times a times b? I even write it like that, a inverse a times b. That's 1, yeah? Definitional multiplicative inverse. Okay. Then from this is a inverse ab, yeah? Yeah? So step by step, this is the definition of the multiplicative identity. That is, 1's the multiplicative identity. It's the thing you can multiply by stuff and not do anything to. It is 1 times b is equal to b. Now, this part here is from the definition of multiplicative inverses. That is, the multiplicative inverse of a is the thing you multiply a by to get to the multiplicative identity. Yeah? Okay. This is from associativity of multiplication. That is, you could regroup your parentheses. Okay. The assumption initially is that AB is equal to 0. So that's from our initial assumption. And then this is item 5. So in either case, A equals 0 or B equals 0 is true whenever AB equals 0. That is, if AB is equal to 0, we did 2 cases. One of them, A is equal to 0. We get the result automatically for free. We're assuming the conclusion in the first case. In the second case, A is not equal to 0. We multiply by its inverse, we get that B is equal to 0. Chapow. Okay, cool. So we proved all of them. It would be wonderful to know if there's a proof of 5 that does not, or a proof of 6 that does not use 5. I would love to see that. If anyone else is able to come up with one, I would be quite happy for you to email it to me or show me next class. That would be very neat. I would love it. We'll also have to modify the homework for Chapter 6, since I'm pretty sure that some of those were problems that I was originally assigning. So, oh well. I guess you'll get a little bit of, free answers there. All right, cool. Or if not free answers, then I'll just cut them off so you don't have to type it up. But okay, cool. So, field. Nice. What about the order axioms? So this is section 6.2. The order of all right, order axioms. So here's the setup. Here's what we're going to set up. Okay. There is an order. We'll write it as less than. Or even, I'll write it this way. I'll present it slightly differently than it's in your packet. Instead of writing them as a set of, I'll write a definition. Let's say let F be a field. We say F is an ordered field. If there exists a relation, we'll write it as less than, on F satisfying the following. 1, if, I'll even write what these are all called as well. This is called transitivity. We've already talked about transitivity for relations, but just to be clear, if A is less than B and B is less than C, A is less than C. Okay, cool. It just, you can chain them together, get strings of inequalities. 2, the trichotomy law. Trichotomy, a word that I'm almost always having to look back at my notes to remember how to spell. For every AB in F, exactly one of the following holds. A, I won't use A, I'll write them. A is less than B. 2, B is less than A. 3, A is equal to B. That is, everything is comparable. You can always say something's bigger or not bigger than something else, yeah? Trichotomy. 3, or are we at the end of the, we are almost at the end. Here. If A is less than B, then A plus C is less than B plus C for all C in the field. That is, it's compatible with the additive structure. And finally, can you imagine what the other compatibility condition will be? Well, a field has 2 operations. It'll probably be the multiplicative structure, yeah? So if A is less than B and C is greater than 0, then AB is less than AC. Oh, sorry, AC. Oh, writing it backwards. AC, BC. That is, multiply both of them by C. Ugh. Instead of adding C to both sides, they multiply C on both sides. Good. Okay. And those are the characteristics for the definition of an ordered field. In fact, the real numbers are an ordered field with the regular old less than sign. Yeah? Kind of great. Okay, cool. We'll talk more about how the ordered structure and the algebraic structure interact nicely next time. Thanks for playing along with me in our fun game of Can We Prove It Together? I'll see you around on Friday. On Friday, remember to bring questions for review and such. So, have a good day.